Hi everybody and welcome to another video of the Optimization Masterclass. So this class is going to be based on the course that I do at Imperial College, which is based on this book, Convex Optimization, of Stephen Boyd and Lieven Vandenberger. If you haven't followed the previous lectures in this series, please check the link over here. Remember that you can download the material that I use to teach the class, so the so-called smart handouts, from the link in the description down below. If you have suggestions on future topics that you would like that I cover in this masterclass, please leave it in the comments below. Thank you very much and enjoy the course. The basic norm approximation problem is the simplest convex optimization problem that we're going to see in this course. This is a very common problem that arises in many different fields. So let's see, for instance, one possibility in which this problem arises. Imagine that you have to produce certain products, and these products are encoded in a vector b. Okay, so you want to achieve this desired objective. The way in which you can achieve this is by a combination of certain design variables. And the way in which the design variables are used is established by a certain protocol which is encoded in a matrix A. So for instance, here what we have is we can select certain design variables x, and these are then combined by a weight matrix A to produce certain results y. And our objective here is to try to make y as close as possible to a vector of targets or desired results. So the way in which this can be achieved is that we can compute the residual error between our AX and our desired objective B. And of course, what we would like here is to try to make our residual as small as possible in a certain sense. So the way in which we can formulate this mathematically is by asking to minimize a norm of AX minus B. And so this is our first optimization problem that we see. And here, I don't specify the norm, so the norm can be different type of norms, okay? So this is a very simple example of unconstrained convex optimization problem. Now, at this point, it's not clear what a convex optimization problem is, and my decision at the moment is not to go into the theory for the first couple of lectures and just look at a lot of different problems. This is the first example, and then study actually the theory after, once we see that there is a huge class of problems that are very important in applications and that we would like to solve. And the common thread here is that all the problems that we will see are convex optimization problems. So this problem is solvable, and there is always at least one optimal solution. The solution is not unique, okay? In some cases it is, but in general it's not unique. We just want to find one solution. We exclude some trivial cases. We exclude the case in which B is in the range of A. Okay, the reason why we exclude that is that if B is in the range of A, it means that there exists a vector x that multiplied by A produces exactly B, and that means that the solution is 0. So the optimal value of the problem is going to be 0. So we already know the solution. The other case that we exclude is the case in which m is equal to n. And we assume also that the rank of the matrix A is full. The reason why we exclude this case is because in that case, if m is equal to n, then the solution is trivial, and the optimal solution, x star, is A inverse times B. So our assumption then is that B does not belong to the range of A, and the other assumption is that m is greater than n. Okay, so this means essentially that we do not have enough design variable to obtain a zero residual. Okay. We also assume, as I said, that A is full rank. If A is not full rank, this is without loss of generality. We can just eliminate some of the equations until you get a full rank matrix A. The problem that we have just seen, it's known as optimal design problem. That's why, because given an desired vector b, we want to design this variable x in order to achieve our desired goal. But this problem of minimizing the norm of ax minus b is actually a very general mathematical problem which arises in many different fields with different underlying meaning. For instance, this problem is also known as a regression problem. And in the regression problem, what we are given is a vector b, and our objective here is to approximate or fit the vector b by using a linear combination of the columns of A. And in that case, then the vectors a1 to an, which are the columns of the matrix A, are called regressors, and the optimal solution applied to our matrix A is going to be called regression of B. The problem also arises in estimation. So another way to interpret this minimization problem is as an estimation problem. For instance, if we are given, so we have imagine that you have a device and you can measure certain quantities of this device. It can be a circuit, for instance, and you measure, for instance, the currents or the voltages in this circuit. So you have these measurements, y, okay? And what you want to know actually some internal variable of your circuit or of your device. And you know that there is a relation, a linear relation between the measurements that you have and the internal variables. So what you want to estimate is x. You know that the x are related to the y by a certain matrix A. But in practice, when you're taking measurements, you're going to also have some noise. Okay, so in reality, when you take measurements y, what you're going to get is, yes, ax, which is the product of the internal variables, the relation between the internal variables and the actual and the output, the measurements, but also you're going to have some noise. And here then you see that what we had with respect to before is that our b is y, and the residual is our noise v. Here the residual is essentially a measurement error, and our objective is to make the measurement noise as the measurement error as small as possible. So the minimization of ax minus b in that case is the problem of finding the most likely variables, internal variables x, that produces that can produce these measurements y, and our concept of best estimate is those estimates that actually are affected the least by a certain measurement noise. Another problem in which another field in which our problem is relevant is the projection problem. So projection problem is a geometric problem, and maybe you're not very familiar with the geometry and geometric problems, but they're actually very practical applications. So let's formulate it and then think about possible applications. Okay, so the way in which it's formulated is that we are given a subspace calligraphic A, and the way of representing a subspace is through the range of a matrix A. Okay, so the range of a matrix A is all the vectors that can be produced by our matrix A. Okay, and what we would like to do here is essentially to, given a point B, which is not in this subspace, we want to project on the subspace. This essentially is asking to find what is the point in the subspace which is closest to B. So you can imagine, for instance, that this is our subspace. We have an external point B, and what we want to find is the closest point to our given point B. Okay, the closest point in the subspace to B. Okay, so it's a projection problem, and as you see, what we're looking at is essentially given our parameterization of the subspace, which is all the vector obtained by A times X, we want that the distance with B is minimized, okay, and is again our problem. And this is a problem in which, for instance, given a certain desired objective B, can be, for instance, certain specification in an industrial plant to produce a certain product, it's possible that those specifications cannot actually achieved. So what we want is, for instance, is the closest achievable specifications. Okay, so you can also imagine that these may be, for instance, a sort of constraint, something that encodes the what is actually possible to achieve. We're given a certain objective B, and then we want to find what is the closest achievable point to B. So up to this point, so we have seen essentially that this problem, this mathematical problem, basic norm approximation problem, arises in different fields. Can be an estimation problem, can be a projection problem, and so on. Now what we're going to look at is some special cases of some usual norms. So the first norm that we're going to look at is the Euclidean norm. Okay, so the Euclidean norm is indicated by the little 2 over here, and actually what we consider here is the squared Euclidean norm. Okay, and this essentially corresponds to what is known as the least square approximation. So the least square approximation is called like this because essentially we know that AX minus B are residuals, and by computing the squared L2 norm, we are essentially computing the sum of the squares of the residuals, and we want to find the least square approximation of B, essentially. Okay, so this is a very well-known problem, and this is a rare problem for which we can compute the solution. This is trivial. I leave it for you as an exercise. The solution is given here. Okay. How do you solve this problem? Well, you just compute the gradient, you set it equal to 0, and you find the solution. Okay. So the next norm that we're going to look at is the supremum norm, which is the L infinity norm. So in the case of the L infinity norm, the way in which the norm is defined is that essentially we're looking at minimizing the maximum absolute value residual. Okay. This is also called the Chebyshev problem or a min-max approximation problem. Min-max because, as I said, you want to minimize the maximum absolute value residual. Okay. Now, as you can see, in general, this problem doesn't seem easy to solve. You know, you cannot solve it as we try to solve the other one because you cannot compute the gradient and so on. But the interesting part here is that this problem can be reformulated as something that is called a linear program, LP. Okay? LPs are a class of problems that we will study in this course. At the moment, I'm not defining what really an LP is. We will look at it in detail later on once we cover a certain amount of theory. But generally speaking, a linear program is an optimization problem in which you have a linear objective and linear constraints. And here, essentially, the claim is that our original problem is equivalent to this LP. And an LP, a linear program, is a convex optimization problem. And so the problem too is a convex optimization problem. Indeed, we will see that from the theory that the general problem that we formulated before with a general norm is going to be a convex optimization problem. And so this has to be a convex optimization problem. But it's interesting to look at a reformulation of this problem as a linear program, and what we obtain is this over here. So let's try to explain it, and then, you need to get used to try to reformulate problems in different ways. So it's good as an exercise to try to understand what's going on here. So remember that what we are trying to achieve is to minimize the maximum absolute value of the residual. Okay, so here what we have is this constraint, okay, and in this constraint we see that ax minus b is a vector of residuals. And then when you do, when you ask that a certain quantity is between, minus something and plus the same thing, is essentially just asking is simply asking that the absolute value of ax minus b is less equal than ti in this case. Okay, this is equivalent to that. And here, let me introduce some notation. So this type of inequality is a component-wise inequality. Okay, so we are doing actually, we are taking each residual, and for each residual, we are doing a component-wise inequality. With t, t here is going to be just a scalar number, and 1 is a vector of ones. Okay, so essentially, this thing over here is nothing else that asking that a residual, let's write it like that, the residual j, okay, is less equal than t, and I mean is less equal than t and greater equal than minus t. Okay, which essentially is asking that the residual j is in absolute value less or equal than t. Okay, so that's just the meaning of this expression over here. And then what you want to do is to minimize this t. And by minimizing this t, you are essentially minimizing, squeezing these inequalities. And the point here is that this is true for all, has to be, this constraint is there for all j's. And the t is the same t. So that means that, of course, what you care about here is just the most restrictive constraint, because if this holds for the most restrictive one, for the biggest rj, absolute value of rj, then it holds also for the other ones. And that's why this is corresponds to the minimization of the maximum absolute value. Okay, so this is a good exercise to try to understand what is the logic behind these reformulations. So let's move on to the next norm, which is the L1 norm. And in the L1 norm, what we are doing is we're minimizing the sum of the absolute values of the residuals. Okay, and I leave it to you as an exercise to think about it, why this problem can be reformulated as this different linear program. Okay, so think about it and try to work it out. Now, we've seen up to this point that our problem essentially has this type our problem has this type of form in which we have a certain we have the sum of powers of residuals to a certain roots. Okay, we can generalize then this objective, considering instead that our residuals are weighted by a certain function phi, which we call penalty function. So a penalty function in our case is going to be a convex function. Again, you don't know what a convex function is, but we will see it later on. So that the problem that we're studying is a convex optimization problem. Okay. So what we already know is the fact that what matters here is the shape of the function. For instance, if we are considering an L2 norm, well, the result is going to be different from an L1 norm. And the difference between the L2 and L1 norm is actually the shape. What doesn't count is, for instance, some multiplication factor. If we want to minimize the L2 norm or 2 times the L2 norm, well, of course, the optimal value is different, but the optimal solution is the same. So the problem is exactly the same. So multiplication for constants do not matter here, but the shape of our function matters. And in which way? Well, for instance, you can imagine that if our function phi is very small, phi of r is very small when r is small, that means that we don't really care about small residuals. If then phi grows very quickly with r, so as r becomes bigger, phi becomes very large, then of course means that we're weighting these residuals, these large residuals, much more. So you see that by shaping the phi, you can obtain different specifications of the residuals. In particular, if you have a function phi that doesn't weight much small residuals, but weights very much larger residuals, you can imagine that these phi's can be, for instance, an L2 norm, okay, so quadratic norm. If instead you have a penalty function that weights all residuals in the same way, then you have an L1 norm, okay, so a straight line. If you consider that certain values of residuals, large values of residuals, are completely unacceptable, then you can imagine that you are using some logarithmic type of penalty function. So let's look at some common examples. And as I said, a common example is the LP norm. Another common example is the dead zone linear penalty function. And in the dead zone linear penalty function, essentially, you have a certain range. Sorry about that. So you have a certain range of u's for which you don't care. So this is minus a and this a, okay? So it's going to have this shape between a and minus a, and then it grows linearly, okay? So this is the dead zone linear, because there is this area here, which is a dead zone where you don't do anything, essentially. You don't care where the residual are inside that dead zone area. Then there is the log barrier penalty function, which is a penalty function in which when you are inside the range plus minus a, you behave more or less quadratically. But then if if your residual is bigger than a, then the result is going to be infinity, and it means that big residuals are unacceptable. Let's look at an example which compares the results of the minimization problem that we have seen for different penalty functions. Okay, so the top plot is using the L1 norm, then we have the L2 norm, then the dead zone linear penalty function, and then the log barrier penalty function. What we're plotting here is the histogram of the residuals in a problem in which n is 30, m is 100, and the matrix A and the vector B are generated randomly, okay? And so what we're seeing here is the histogram, so essentially it's telling you how many residuals there are for each value. And we see, for instance, that for the L1 norm, we have a lot of residuals with value 0, okay? And then we have, residuals that are non-zero, which are spread more or less everywhere. You also have very large residuals, for instance. For the L2 norm, what we see is that you don't have residuals which are 0. I mean, you have some, but not many. And then you have a concentration of residuals around 0, and very few residuals which are large, okay? For the dead zone, we see that there is a concentration of residuals at the moment in which the dead zone ends. You have some residual inside, and also some residual outside are acceptable. And for the log barrier, you see that the distribution is very similar to the L2 norm distribution for around 0, but values of residuals larger than plus minus 1 are unacceptable and they are not present. Okay. Now, what is the point here? The point here is that, and this is an important message, is that an optimization problem usually is not given to you. It's not something that, when you're working, someone comes to you and says, solve this problem. No, I mean, you are probably working in a certain field. It can be electronics, it can be computing, it can be finance, it can be anything, essentially. And at a certain point in your working life, you may be asked to find the best solution. So to find to solve an optimization problem. And now, I mean, it's not that someone tells you, this is the problem that you have to solve, this is the function, the penalty function. No, it's up to you to decide what is that you care about. And formulation of the problem, formulation of the optimization problem, is a very important part of solving optimization problems. Because depending on how you formulate a problem, you may have a solution or not, for instance, or the solution may have a different meaning. And the other important message is that the solution of the convex optimization problem, or in general of an optimization problem, depends on how you design the problem. And in this case, we are looking, for instance, at penalty functions. And, you know, whatever penalty function you use, you're getting a solution. But the property of the solutions are different. And understanding what a certain penalty function provides you is important. Okay? So it depends what you're trying to achieve, what is your problem, your practical problem. Depending on that, then you pick, for instance, the penalty function. So let's look again at these 4 plots, and let's try to understand when to use one and when to use another penalty function. Well, for instance, if we want a sparse solution, so a solution in which the majority of the residuals are 0, then we want to use the L1 norm. Okay, so for some reason, we don't care of the value of the residual, so it can be also big. The only thing we care about is that there are not many residuals. Okay, so that we try to decrease the number of errors, essentially. Let's try to understand also why the L1 norm has this property of producing a large number of 0 residuals. Well, you can imagine that the way in which this function works is that they are pushing the residuals towards 0 based on the slope of the penalty function. And you see that the important property of the L1 norm is that it doesn't matter where you are, you always have the same slope. So there is always the same push to go towards 0. And this means that all the residuals, are pushed towards 0. If you go to 0.1, you still have an incentive to go to 0.01 and so on towards 0. This is not the case for the L2 norm, because in the L2 norm case, we have a strong slope for large value of the residual, so there is a strong push to go towards 0. But once we are close to 0, the slope becomes flat, and there is no incentive to actually push the residual to 0. So that's why they have different property. This also explains the behavior of the dead zone. Okay, so in the dead zone, we have a constant slope until the beginning of the dead zone. So a lot of residual accumulate over there, but then we don't care at all about what happens after. And so there are some residuals there. They may be there or they may not be there. But the fact that the residual is here, a lot of residuals are here instead of here, it's totally random. Okay. And again, for the log barrier, well, we may have a case in which certain errors are totally unacceptable. You really care about the fact that you don't want large errors, and that's why you use a log barrier function. So the key message here is that picking the penalty function is part of the design of the problem. It's a choice that you make, and you should make this choice depending on what is that you care about. So very related to what we discussed, it's what happens if, for instance, you have few residuals which are very large. So they can be considered as outliers. They can be considered as errors. Okay. So you have a certain distribution, like for instance, let's look at this figure here. Okay. So here you have 42 points, and what you want to find is a line that goes through the points. Okay. Now, the problem is that we have, so you can imagine that these are measurements, that you have two measurements which are very, very far away. Okay? And here, if you look at the residual, you see that this residual is very large. Now, if we use, for instance, an L2 norm, well, the L2 norm is going to very dislike this residual. Okay, so the L2 norm really dislikes this residual, is going to try to minimize it, and this is going to produce this dashed line over here. So the dashed line is produced by the L2 norm here. But we see that actually we don't want that. I mean, we see that the approximation here is bad, okay, because we clearly see that the line should be actually this line, you know, the line that goes through the points, okay, so the solid line. So how to do that? Well, in that case, we can use a penalty function which is called the Huber penalty function. It works very well in practice, so that's why you should be aware of it. And essentially, the way in which it works is that if the residual is smaller than a certain large value, then we use an L2 norm. But if the residual is bigger, then we consider it an outlier, and instead of using a quadratic penalty function, we use a linear penalty function. So we still don't want large residuals, but we don't weight them as much as an L2 norm. Okay, and the result is here. So as you see in this problem in which there are outliers, the Huber penalty function, which is the solid line, works much better than the L2 norm. We already discussed about the fact that the L1 norm produces a lot of residuals which are 0, okay? And this is an important property of the L1 norm, okay? So the L1 norm, it's a very important norm. It also produces robust results, as we will see later. But for now, for instance, we already seen very clearly that the L1 norm produces sparse solutions. Sparse solutions is solutions with a lot of zeros. And we, again, may be interested in sparse solutions because of some physical meaning of the variable that we are trying to optimize. Now, up to this point, I spoke about the basic minimization problem of the norm of ax minus b, but of course we can add constraints to it. And let's look at some typical constraints that are associated to that specific problem. For instance, we may have non-negativity constraints. So we may require that the variable x, all the components, so component-wise, all the components are positive. Well, this is the case, for instance, if our x has some physical meaning for which we know that they have to be positive values, otherwise they wouldn't make any sense. This could be, for instance, powers, intensities, rates. So everything that we know for sure that has to be positive, we definitely want to add this constraint. Another possibility is another common type of constraint for this problem is the variable bounds constraint. So we say essentially that our component xj has to be between a certain bound lj and uj. Another common type of constraint is a constraint that tells us that our variable x is a probability. And that means essentially that the values has to be positive and has to sum to 1. Okay, so the total probability has to be 1. Another common constraint that appears in these problems is the norm ball constraints with center x0 and radius d. And essentially what we are asking is that, okay, what is the idea here? The idea here is that we have a good guess of what x should be. And we say, okay, I think that x should be this value x0. Of course, I'm not sure about that. That's why we're doing the optimization, the minimization in this case. But we have a good guess. And we also know that the solution cannot be too far away from this guess, okay? And so we formulate this type of constraint in which we say, okay, we want that our x is inside a ball of radius d, which is our trust region, okay, of centered in x0. Okay, so actually the ball, as I said, represents a trust region, and one way to interpret this problem, I mean, one possible way in which this problem arises, is when we know that a times x is a good model of our underlying function f of x, which however is nonlinear. So we said, for instance, that we were estimating in the estimation problem, we were saying that we were measuring y, and y is the product of some internal variables which are related linearly by a matrix A to y. But in general, the relation may be nonlinear. Nonlinear maybe is difficult to deal with, so we want to linearize. We find this matrix A, which is a linearization. But linearization, it's local. I mean, it gives you a local model. It works well around the point in which you linearized. If you go too far away, the model, the approximation A times x, is not good anymore. And in that case, then it makes sense to say that, yes, I want to solve this minimization problem, ax minus b in norm has to be minimized. But since my model is being linearized around this point x0, I want to have the constraint that the solution cannot be too far away from x0. Because if that's the case, then the solution is meaningless, because I'm minimizing a model which is not a good approximation of my underlying model.